Good morning, everyone. Today we want to look at the concluding part of our chapter 15, and we'll begin with the topic energy and intensity. We'll be discussing that amongst other subheadings, just to conclude that chapter of traveling waves. Okay. So we want to look at energy and intensity with respect to circular, spherical, and plane waves. Okay. So we'll have circular waves, we'll have spherical waves, and we'll have plane waves. And we want to look at relationship of the energy of traveling waves and the intensity for these three types of waves. If we look closely at the diagram before us, we see that the wave front are the crests of the wave. The line you are seeing, the circular line, they are the crest of the wave, and they are spaced one wavelength apart. Okay. So you see, the spacing is one wavelength apart from the source. And the circular wave is going in all directions from the source. Okay. So the circular wave front moves outward from the source at speed v. And a good example is dropping an object in water. You will see practically the wave spreading out from the source, and the crest is what we're using the defined lines to represent. Okay, so if we have very wide spread out at the extreme end of the wave, if you take a portion of it, it appears as if they are straight lines, and that is the figure we have represented in the figure B. The very far away from the source, small section of the wave front appear to be a straight line. Okay, so it is curved, but if you take a snapshot of a section, it appears to be straight line with the same wavelength spacing, and spreading out in that direction. So a traveling wave transfer energy from one point to another. I've seen that and emphasized that before. The power of the wave is the rate in joules per seconds at which the wave transfer energy. And we measure the power also in the units called watts. We have several waves, such as sound and light waves, that move in 3 dimensions, but for the circular wave, it's actually moving in 2 dimensions. So the circular wave is 2-dimensional, but the sound wave and the light wave are typical examples of 3-dimensional wave motion. Okay. So speaking about 3-dimensional wave motion, we want to look quickly at the motion of the light bulb, which is actually a spherical wave. Remember, we're looking at the circular, spherical, and plane. All right, we have emphasized that for the circular wave at the extreme end, when they are spreading out, if you take a portion, you look at it, it's going to appear like a straight line. All right, that is not the description of the plane wave we want to refer to. We'll see that later. So the loudspeaker and your light bulb emits spherical wave. Okay, let me say emits a kind of 3-dimensional wave. The crest of the wave forms a series of spherical shell separated by the wavelength. The spherical is a little bit away from circular shape. And in essence, we are emphasizing that it is a three-dimensional ripples. Okay, so let's look at the diagram before us. At the very far end of the source, the small segment of spherical wave also appears like a plane. So they appear like as if they are straight, but it's going to appear like a plane. The wave is cresting at every point in the plane. Look at the wave. You see the crest, the top is cresting at every point that appears like a plane. And we also have the wavelength as the interval apart from this plane. So while we have the representation appearing like a straight line in circular shape or circular wave, we have that of the spherical. When you view it very far from the source, a portion of it appears to be like a plane where the crest of each of the wave is crossing the plane. So if you observe a spherical wave far from its source, the small piece of the wave front that you can see is a little patch on the surface of a large sphere, but it's going to appear to you like a plane. So if the radius of the sphere is large, you will not notice the curvatures. You will not see if the shape is actually curved because the portion you are going to be looking at will appear like a plane. And that is the idea of the plane wave we'll be looking at later. Okay. So having established that the spherical is three-dimensional and the circular is two-dimensional, we want to proceed to looking at the discussion of their power, energy, and intensity. What do we mean by that? How do we describe wave using these three parameters? When a wave has a power P, we define the intensity of that wave as intensity being equal to power per unit area. We're using the small letter A to describe area here so that we'll not confuse it for amplitude, capital letter A, okay? So the area, small letter A, is area here. And the SI unit for intensity is given by the watts per meter square, right? So if a wave has the power P, the intensity is given as P over A. And if we look at the figure before us here, we'll see the plane wave of the power impinged on an area A. This is the plane wave, like we saw in the description of the plane wave idea we saw earlier for the section far from the source of spherical wave source. We see the plane waves, each of the plane being separated by the wavelength lambda, and the direction of the wave is to your left. Then we'll have the wave intensity at the surface to be given as P over A, and this is the area of that plane. Okay, so because the intensity is the power to area ratio, the wave concentration onto a small area has a higher intensity than the wave of equal power that is spread out in a large area. It's like lighting up your small room with the same bulb that has, let's say you're lighting up your room with a 9-watt bulb, energy saving bulb, and then you take the same bulb to a bigger room like your parlor. You find out that the light in your room appears to be having higher intensity or shining brighter, but the same power or the same bulb when taken to a broader room tend not to shine or cover everywhere. So we can emphasize that the large area has influence on the intensity. The area of the wave or plane wave has influence on the intensity. So let's quickly look at an example. A bright, tightly focused laser pointer emits 1.0 milliwatts of light power into a beam that is 1 millimeter in diameter. What is the intensity of the laser beam? Okay, using our formula for intensity, the power is given to us as 1 milliwatts, and if we convert that to watts, we'll have 0.0010 watts. And the area for this beam is given as pi radius squared, right? So pi is a constant, and if the radius is the diameter is given, and if we take the radius, convert it to meter, that's divided by 2, then convert to meter, we'll have 0.005 meter squared. And multiplying that out, we have 1,300 watts meter squared to be the intensity of the laser beam. Okay. All right, so that's simply the application. We can use that to solve physical problems just as represented here. So looking at a source emitting uniform spherical wave, I'm still discussing circular, spherical, and plane wave. If we have a source emitting uniform spherical wave, the sphere is more close to a circle, but a little away from a circle, okay? So if we have this source with the power P source, and then we'll have the cross section of the spherical wave front, which is the crest. And then we'll have the energy from the source spreading out uniformly all over. And the area of a sphere is given as 4 pi r squared. The spreading out from this source uniformly outward, we're emphasizing that the intensity is dependent on the distance, r, okay? And that's what we want to establish here. We look at the distance r here from the source, that's to the second crest. We have another distance from the source to about the fourth crest. The intensity I1 at distance R1 when compared to the intensity I2 at distance R2, we'll be able to tell from the formula the relationship of intensity to the distance. Now let's look at that in this formula. When, for example, the sound from a speaker, which is a typical example of the wave, a spherical wave form, the sound from your loudspeaker and the light from your light bulb become less intense as you get farther from the source. And the relationship of the intensity, which is given as power over area. If we have defined the power to be the P source and the area also to be 4 pi r squared, which is the area of a sphere. The intensity of the distance r of a spherical wave from the source is given as I equal to P source over 4 pi squared. What we mean by that is the intensity has the inverse square dependence on the distance r. Okay, you can see It's inversely proportional to the distance r, the square of the distance r. So consequently, the energy per unit area must decrease in proportion to the surface area of the sphere. Okay, so the surface area has influence on the intensity, and that's a typical example of what we said, that the same power, the lesser the area, the more intense you will see the wave appear, but the broader, the less intense. Okay, so we said as it go further, it becomes less intense, and that relationship is the inverse square dependence on the distance. So if we have two systems and want to compare the intensity of the two distance from the source without needing to know the power of the source, we can use the formula, the relationship I1 over I2 being equal to R squared 2 over R1 squared as well. Okay, so this is when we want to look for or compare the intensity between two sources when we don't have to know the power. Okay, so let's see an example. The intensity of a sunlight on the Earth's surface is approximately 1000 watt per meter square at noon on a summer day. Mars orbits at a distance from the sun approximately 1.5 times that of the Earth. Good. A, assuming similar absorption of energy by the Martian atmosphere, what would you predict for the intensity of sunlight at noon during the Martian summer? B, the Sojourner rover, an early Mars rover, had a rectangular array of solar cells approximately 0.6 meters long and 0.37 meters wide. What is the maximum solar energy this array could capture? C, if we assume a solar to electric conversion efficiency of 18%, typical of high quality solar cell, what is the maximum useful power of the solar cell? Useful power the solar cell could produce. So let's see how we use the information we have about intensity and power to solving this problem. In the first case, we are asked, what would you predict the intensity to be? All right, so they gave us two systems. We have that of the Earth and that of the Mars. Remember the intensity relationship that we quoted earlier? For T1, T2 will be equal to R squared 2 over R1 squared, right? So if mass is your T intensity 1 and Earth and mass, if you make that mass the subject of formula, you have this cross multiplying and dividing by the coefficient of mass. So we'll have, making that subject of formula, that's how hard we got this expression. Substituting directly from the information provided in the question, they gave us the intensity on the sunny day to be 1000, intensity of sunlight to be 1000 watts, and the distance to be 1.5 times that of the Earth, which we substitute into this equation directly to get the intensity of the mass on a sunny day to be 440 watts per meter squared. So proceeding to solving the second problem, we want to calculate the energy that the solar cell can capture. Okay, So from our formula for intensity, which is I over PA, I P A. So your P will be equal to IA, intensity over area, right? And the area of the panel given to us to give us the length times breadth. So that's how we got this. For the area of the solar array, the length was given to us and the width was given to us. We got the area. Substituting that directly into our intensity formula, making power the subject of formula because they asked us to look for the rates, the energy that solar can capture. So put that in, we have our area, intensity also calculated from this first, from our question A. So we'll have I times A to give us 100 watts. And that tells us that 100 watts simply tells us that the cell captured solar energy of the rate 100 joules per second. That's the meaning of 100 watts here. So to solve the problem C, we established that not all these energies are converted to electricity. So we were given that it has 18% efficiency. So if it has 18% efficiency, that will give us the information on the energy that is converted to electricity. So multiplying the 100 watts by 18% efficiency, we're able to get 18 watts, which is the energy converted to electricity at this efficiency rate. Okay, so we'll see that we can use the power information and equation to get other information about the usefulness of the relationship between intensity and energy output for systems. Okay, so we'll have this class activity and I expect you to look at it critically and see if you agree with the answer provided or not. If you have any reason to dispute the answer, you can send me a mail and we'll talk about it, okay? So let's move on to another subheading of this last part, which is loudness of sound. Loudness of sound. When we say loudness of sound, what do we mean? The loudness of sound is measured by a quantity called sound intensity level. Okay, we have looked at energy and intensity, and now we want to look at loudness of sound. And the only way we describe the loudness of sound is with the quantity called sound intensity level. So the unit of sound intensity level is decibel. Okay, decibel is represented with dB, small letter d, and B, capital letter B. So we have established that we use what we call sound intensity level to describe the loudness of sound. And we also want to say that sound itself has different range. The range you can hear as human, we mentioned it earlier, from 20 to 20,000 decibel thereabouts. We have the range that humans can hear, we have range for animals, and so on. So we'll compute sound intensity level from the relationship described as the relative intensity for sound intensity level and the intensity itself. So sound intensity level in decibel is represented with the beta sign here, which is equal to 10 decibel, that's 10 to log base 10 intensity over the smallest intensity that human can sense, which is I naught, and that is giving us 1.0 times 10 raised to the power minus 12 watt meter squared, watt per meter squared. This is a constant. That is the least or smallest intensity that sound the human can hear. And this relationship is what we use to calculate the sound intensity level. Okay, so we can also compute the intensity from the sound intensity level by taking the making intensity the subject of formula in this relationship, and then you take the logarithm base 10 to have exponential b 10 decibel, right? So we'll have range, established constants or range in decibel and intensity for sound. We look at that of one common to us, humans, right? We have different, this is the threshold for hearing for human, and we'll have for person breathing at 3 meters. We'll have for whisper, sound in classroom for different environments. And this is the standard formula for sound intensity level as described decibel in relationship to the sound intensity I. Let's see an example to see how we apply that to solving physical problems. A person shouting at the top of his lungs emits about 1.0 watts of energy as sound wave. What is the sound intensity level 1 meter from such a person? If you're standing 1 meter from such a person, what is the sound intensity level? Okay, so the distance from such a person is given as 1 meter, and the sound intensity level using this formula. First, we'll use this formula to calculate the intensity because we know at this end, intensity over that's what is here. So from our formula given, the intensity equal to power over area, the distance is given as 1 meter, and then taking the square root of that plus the power in watts, we have the intensity to be 0.80 watts meter squared. Now substituting this into the formula for sound intensity level, which is your beta equal to 10 decibel log 10 intensity over the smallest intensity that human can hear. So intensity I over I naught, we substitute directly with the values given. We know this. This is a constant from that table. And we have log 10 of this value in bracket multiplied by 10 to get 110 decibel. So this is the sound intensity level of that person at that distance. Okay. So we proceed quickly to another interesting topic as well, the subheading, the Doppler effect and shock waves. Now, Doppler effect is something we experience every day. We really, sometimes when if you're driving or you're walking, you hear a siren coming towards you. As it approaches towards you, it gets louder, and as it passes, you see the sound begin to fade away. So you see that there's a kind of change in frequency that you observed from the sound that comes to you. So the change in frequency, which is due to the motion of that ambulance, that is the siren of the ambulance coming or approaching and also passing by. That change in frequency is what we call Doppler effect. Okay, that's what we call Doppler effect. So simply put, Doppler effect is the change in frequency when a source moves relative to an observer. The source is either approaching or passing by, or the observer is approaching the source or passing by it. There's a change in frequency, a change in the sound you hear, the intensity of the sound you hear. That change is what we describe with the word Doppler effect. Now, Doppler effect happens quite all right in our everyday life. So also is what we call the shock wave. Now, shock wave is a kind of a more interesting aspect of Doppler effect. It's actually a scenario where an object is moving faster than the speed of sound that it emits. Okay, so somewhere down this lecture we said it's outrunning its source. All right, so it emits sound, emits a wave, and also move faster than what was emitted. When that happens, that system experiences what we call the shock wave. And that's what we see when you crack a whip and it produces from the tip the supersonic speed. We will look at the shock wave again, but it's simply shock wave happens when the speed, the source or object is moving faster than the speed of wave produced. Okay. So let's see the sound wave from a moving source. I want to buttress this, what to mean by Doppler effect and shock wave. That's what we want to look at in details. We have the sound wave from a moving source. For example, in this figure A here, the motion of the source, we see that the man Pablo and the lady Nancy. The dot sign here represents the position of the source at different time. Okay, so the source emits the frequency Fs, that is frequency of source. Then we see that the Pablo sees the source receding from his end, while Nancy will be seeing the source approaching towards her end. Okay, because the source is going this way. So the velocity of the source is moving from 0 to 3. But the dots representing different instance or time of that movement. Okay, so as the source is receding from Pablo, it is actually approaching Nancy. So let's see what actually happens in details when we take a snapshot at different time of that motion. The kind of change in frequency that is observed is what we want to really look at. So behind the source, the wavelength expands. When the source is receding from you, or is going away, farther away from you, you see that the wavelength appears to be wide. When it's approaching you, the wavelength is positive, that is smaller. So we have wavelength negative, and then we'll have the positive when it's approaching. When it's receding, it's negative. So we see that the crest at 0 was emitted at time 0, and the wave is the circle center at 0. This is 0 point. This is the crest, the red at 0, red to go with red. So that's the wave emitted, and this is the distance, 3 lambda naught. So at crest 1, which is the green dot, and tallying with the circle green, we see that it was emitted at time t, and the wave front is the circle center at that point 1. Same goes to B for 2T. The wave the center to this blue line, and the center is at T2. Okay, so we notice that as it retreats from Pablo, the frequency, the wavelengths, they are wider, and the frequency is also minus, just like the lambda is minus, but when it's approaching, it's plus, as the lambda is plus. So the motion of the source cannot affect the wave that's already emitted. That is what it means here. The wave is already emitted. If the source keep moving, it's not going to affect this wave. Okay, it's emitted, it exists, and it starts traveling. And that is how, as it's moving, it keeps emitting wave. So each circular wave, as seen in this figure, has its own center, because as it is going, it's emitting wave, and the motion of that source does not affect the emitted wave. But what we feel when it's receding, and when it's approaching is what we have observed with the lambda plus and frequency plus. Okay. So the frequency heard by a stationary observer actually depends on whether the observer sees the source approaching or receding. If the source is approaching the observer, the frequency is given as F plus equal to the frequency of the source over 1 minus the velocity of the source over the speed of the wave, the speed of the source over the speed of the wave. Okay, if it is receding, note the sign, because this is where the difference is. We observe that the frequency increases when it's approaching, but when it's receding, the frequency will decrease. That's why you have minus here and plus here. So you have a plus sign for this. The frequency of the source over 1 plus the speed of the wave, the speed of the source, and the speed of the wave. Okay. So let's take an example to buttress that. A police siren has a frequency of 550 Hz. As the police car approaches you, 450 Hz after it has passed you and is moving away, how fast are the police traveling? So we know the frequency when it was approaching, and then we know the frequency also after it has passed. The question is how far? How fast are they traveling? So from the equation given earlier for the frequency here, if you make this the subject of formula, that's what we did to get this expression for the frequency when it's receding and for the frequency when it is approaching. So now that we have the frequency when it's receding and when it's approaching, we want to know how fast the police is traveling. So given these two, approaching and receding, we want to subtract the second equation from the first, that is subtracting this from this. We'll have Fs minus Fs to give us 0. Then we'll have on this side, if you open this bracket with the Fs, you will have F minus something like that, Vs over V, okay? And for this one, you will have the plus as well. So F plus minus V S over V. Okay, let me clean that and write it clearly. All right. So we'll have, if you open this bracket, we are opening up this bracket, F minus plus Vs over V F minus. Then for this side, we'll have F plus minus, Vs over V F plus. All right, so we have this minus Fs to give you 0. Then we'll now have F minus minus F plus for this. Okay, remember you're minusing this. Then for this, we'll have, they are common to each other. So we'll have Vs over V into F minus give you plus. So that's how we got this expression here. So the V is common, and then this minus minus this will give you plus. So that's how we got the plus here. So I haven't gotten this expression. We want to make V as the subject of formula. So we'll move this to cross the sign of equality. And then divide by the coefficient of Vs, which is this over V. So we made V as the subject of formula, we obtain this. We substitute directly into the question. Fs, when it's plus 450 minus 550 will give you 100. Then when you add 450 plus 550, you have 1000. Then V, which is the speed of the wave, is a constant, 343 meters. Multiplying directly will have the value to be 34 meters per second, and that is the speed of the source. That's how fast the police are traveling. They are the source. Okay. So quickly, let's proceed to looking at the stationary source and the moving observer. Okay. Remember, we looked at the observer approaching before, and now it is the previously we looked at the observer being stationary, the source approaching and passing by, but now we want to look at when a scenario when the source is stationary and the observer is the one approaching and also passing by. So we have the same representation typically, but the only difference here is notation for the observer instead of the source. So with speed of the observer over the speed of the wave, the frequency when it's approaching, and that is the frequency of the source as well, and when it's receding. So it's the same way we apply it as well for solving problems. When it's emphasized that the observer is the one that is in motion, you use these two equations. But when it is the other way around, which is the source that is in motion, use the previous equation as we have applied earlier. So let's see another one, the Doppler effect for light waves. We have seen Doppler effect to be the frequency, the change in frequency, all right, as it relates to the observer. How do we view Doppler effect when it comes to light waves? Remember, light wave is a 3D kind of wave representation, and we have also seen the description of light waves in spherical waveform. So if a source of a light wave is receding from you, the wavelength will have the negative sign, and you will detect that the wavelengths tend to be longer, just like we saw in that description. When it's receding or going away from you, you see the wavelength is longer and represented by the minus sign. And the interesting thing about the description of Doppler effect with light wave is that the wavelength is actually shifted towards the red end of the visible spectrum. And this is what we call the red shift. So we experience what we call the red shift when the light wave is receding from you. But when it is coming towards you, we experience what we call the blue shift. And that is typified by shorter wavelengths. When you picture the diagram you saw earlier, for the Nancy part, you see short wavelength. Yes, short wavelength, then you see the frequency, everything is getting shorter as they come close, but when they recede, it gets larger and bigger. So for object moving at normal speed, there's no or typically no difference. The small effect is such that it's not noticeable. So you won't see the Doppler shifts and the flashing of light. Okay. So we see also the example of the police car and the siren. All right. So for wavelengths, Doppler effect in light, we want to emphasize the red shift and the blue shift description. The red shift typifying when it's receding from you, and the blue shift when it is approaching. And when it is moving at normal speed, you don't see any Doppler shifts. All right, just take note of those points. So the frequency shift on reflection from a moving object. Let's quickly run through that, and then we'll take few examples and we'll be done. Okay, so when we say frequency shift on reflection from a moving object, when a wave actually is emitted from the source and it hits a barrier or obstacle, it can reflect back. And the source is going to view that wave like a new source. When it comes to sound, the reflected wave is regarded as echo for sound wave. It comes back to us as echo. Okay, so the wave reflected back towards the sound source by the moving object is also a kind of Doppler shift to a higher frequency because the source is going to view the reflected wave as a coming, is going to view the reflected wave as coming from an object. Okay, so the frequency shift of the wave reflected back from an object is given as change in frequency plus or minus 2 f s v naught over v. Okay, so change in frequency plus or minus 2, the frequency of the source, the speed of the object, and the speed of the wave. All right, so I have the assignment 2 here. So you also be solving these 2 assignments plus the one I'll be adding from the problem set, and I'll post it on Moodle. Okay. These 2 slides describe the same assignment. So let's look at the last part of this course and this topic, which is shock wave. We've seen the introduction of shock wave before. We said that the source is outrun when the source outrun the wave it produces. When we talked about Doppler effect, we said that the change in frequency, but there's a case or a scenario when the wave produced by the source is actually moving faster than the wave it's producing. And this actually happens mostly in a typical example of speedboat traveling in water. You see the V shape forming behind the boat. So the shock wave is typified actually by V shape when it's manifesting in the physical, especially for speedboats traveling on water. You see that V shape. What actually happens is that the amplitude combine with the shock amplitude produced. So the crest is really high visible and it forms that V shape behind that boat. Okay, so let's see a representation of the wave emitted by the source and is traveling faster than the speed of the wave that it produces. Let's see this figure and a couple of two other figures to buttress this point. The source of the wave is moving to the right as typified by this arrow. Now the position for different time is what will mark from 0 to 7. At each point, the source emits a wave and they spread out. When you take a snapshot at different points, you have the representation as captured below. So we take the snapshot at T7, and this is exactly what happens at that time. The crests on number 3, let's see, this is the 3 crests with the purple sign and the circle, purple circle there, with the distance r being 4 lambda. Remember that we said whenever a wave is produced, the motion of the source does not really affect that because the wave has been produced, it continues traveling. So the crest produced at, the third crest produced at 3t with the speed, with 40 before the snapshot. Our focus is on this purple and this purple circle. The wave front is that circle with the radius, and that's the center. And as it produces, the source tends to move faster than that wave. Okay, so the source speed is greater than what it has produced. It's already covering that distance almost immediately, such that during the time T4, since the third crest was emitted, the source has moved further from the third crest. It has moved further beyond the third crest. After emitting the third crest, it has moved to 4, 5. So you see other circles forming, and then the wave produced also forming its motion. And then they combine, like I was saying, the amplitude combine that with that of the wave produced and the speed to give you the V shape behind the source as it is moving. So assuming this is the speedboat, you see the water forming that V shape behind the boat. So the wave crests, they all overlap. And as they overlap, the crest is bigger and they form the V shape. And it is a V shape that we refer to as the shock wave that travels as the wave speed also travels from the source. Okay, so this happens so fast that that motion is what gives that V shape behind the speedboat. Okay, so that's the idea of what we mean by shock wave, the kind of wave that is produced when the source is traveling faster than the wave produced. Okay, so that's the last part of this chapter 15. And next week we should proceed to chapter 16, and I'll be posting the assignment for this chapter and the due date as well. The due date for the first assignment will be adjusted and the corrected video also will come up today. All right. So thank you so much. I look forward to receiving your comments, question on the discussion so far. Do have a great day. Bye-bye.